What's up geeks, and welcome to the channel. Say you have a singly linked list represented by the node class you see in front of you. This list contains multiple nodes storing different values, and our goal is to find the middle node of this list. Now, if this list was represented by an array instead of a head node, what we'd have done is find out the index of the last element in that array in constant time, and then return the value located at the middle index also in constant time. However, here we have a linked list, and if we were to take a similar approach to the array, we'll have to iterate over the list once to find the number of elements it contains, or its length, and then we'll need to traverse half of these nodes a second time while stopping at the middle node to return it. This works, but this is not optimal. And before tackling the optimal solution, let's take another example. And suppose we have this array of numbers sorted in ascending order. What we want to do here is try to find any two numbers such as they add up to a specific given target number, let's say 25. Now, a trivial solution here could be to loop over this array twice, allowing us to compare each element in this array to every other element in the same array. And as soon as we find a solution, we return it. This works, but this has a quadratic time complexity, and as you may have guessed, is definitely not optimal. So how do we solve these problems or similar problems? How do we approach them in an optimal way? Well, today's video is all about answering these questions, and the short answer here is the two pointers approach. As its name suggests, the two pointers approach allows us to keep track simultaneously of two elements inside a given array, allowing us to process two elements per iteration instead of one. And the two most common templates involved in this approach are: one of the pointers moves at a slow pace while the other pointer moves at a faster pace, or one pointer starts from the beginning while the other pointer starts from the end until they both meet. Now, we are going to make use of these templates respectively to solve the problems we had at the beginning. Let's start with the linked list problem, and suppose we have two pointers, slow and fast, both pointing to the head node of the list. Now, one of these pointers, the slow one, will traverse this list normally by hopping one node at a time, whereas the second pointer, the fast one, will hop two nodes at a time. Notice that by the time the fast pointer reaches the end of the list, the slow pointer will be located exactly at the middle node of the list, which is exactly the element we are looking for. And that will always be the case because one node is moving twice as fast as the other node. To implement this, all we have to do is create two nodes, both pointing to the head node, which is our starting point, and then while the fast pointer hasn't reached the end of the list yet, we update the slow and fast pointers to hop one node or two nodes at a time, respectively. When the end of the list is reached, we return the node stored inside the slow variable, as it is the one located at the middle of the list. And that's it, and that is optimal. Now on to the second problem. Let's bring back our sorted array and that quadratic solution we had. You see, the main problem with that solution is we didn't make use of the sorted constraint that was given to us. So how do we do that? Well, consider these two pointers, one pointing to the beginning of the array and the other one to the end of the array. If we add the values at these pointers or indices, we will get 32, but the target sum we are looking for is 25. So that sum we obtained needs to be reduced, and given our layout, we have two choices: either increase the left pointer or decrease the right one. Those are our only two moves, right? Now, if we increase the left pointer, the sum will increase as well. You see, the array is sorted, therefore the element located at left plus 1 is bigger than the element at left. But if we decrease the right pointer, this sum will decrease as well, as the element located at right minus 1 is smaller than the one at the right, and that is exactly what we want. So, if the sum of the values is less than the target value, we increment the left pointer, and if the sum is higher than the target value, we decrement the right pointer. We'll keep moving these pointers until we get the sum that matches the target value, or until we reach the middle of the array, meaning no combinations have been found. To implement this, we'll start by initializing our two pointers, and while these pointers are different, or left is still smaller than right, meaning we still haven't reached the middle of the array, we are going to add up the values located at these indices and check if that sum is smaller than our target value, we increment the left pointer. If that sum is bigger than our target value, we decrement the right pointer, and finally, if the sum is equal to our target, we simply return with the matched result. And that's it. And that runs in linear time, which is a significant improvement over our first implementation. Now, while trying to explain the two pointers approach, we managed to solve two LeetCode problems, to which I'll leave the link down in the description below. Let us know in the comments as well which topics/problems you'd like us to tackle next and see in this series. So that's it for this video. I hope it was helpful. Thank you guys for watching. Take care and I will see you in the next one.